Hey everyone, welcome back to MLWorks. In this video, we'll be continuing with our series on visual introduction to deep learning. Previously, we were talking about how to build a neural network with single neuron, and that was for a specific use case for linear regression. And now what we'll do is we'll move ahead and talk about non-linear regression, because most of the practical scenarios that we see in industry is containing non-linear relationship between the features and the target. So we want to understand that with the help of deep neural networks. So basically this is how a non-linear relationship looks like between feature and target, and we want to understand or build a neural network which will try to capture this graph. Now let's talk about what is neural network. A neural network is a building block of neurons where each neuron capable of learning something on its own, and when the whole network is combined together, it will try to understand one specific task. So a neural network consists of layers where you have input layer, output layer, hidden layer. Hidden layer is where you will be trying to learn something about input and that is input and target, or features and target, and you will learn the relationship and try to update those relationships in those neurons. So the number of neurons per layers can vary. That depends on the type of task you have, and if it is an autoencoder, you will have a bottleneck layer where you will have less number of neurons, and if you have something like a computer vision kind of a problem, you will have large number of neurons across the layers. So it depends on the type of task you have. Like if it is a complex task like computer vision or natural language processing, then the number of hidden layers will increase. Also, the number of neurons per layer will also increase. Now let's understand a simple example of neural network. So consider you have a neural network with two hidden layers, and each layer containing three neurons, and we have three inputs, which is here, and those get connected to your hidden layer ABC, and which gets connected to DEF. Now if you want to understand, the neuron A takes in three inputs from three, that is x1, x2, x3. Now the output from that specific neuron, which is A, it will generate three outputs. So that will be sent to neuron DEF. So when it comes to E, again it takes three inputs, which from A, B, C, and it will generate an output which will be sent to the output layer. Now let's talk about what happens in each neuron. So basically there are two mathematical operations that is getting done in the each neuron. One is weighted sum, which is your input into the weight, then plus bias, which will give you z value, and then you have activation function. In previous cases we were using linear activation, which will change in this scenario. So the goal for this specific video is to do predict hotel room rate prediction, and we have distance. Earlier we also had distance as a feature. Now along with that we also have ratings per hotel. So we use these two features to predict what is the price for a hotel room. And the data set that we have is around 40 data points, out of which 32 training sets will be used for training set, and 8 of those will be used for testing set. And this is the distance and ratings and corresponding price. Now if we plot the graph between distance and price, this is how it looks. Okay, there is no like purely increasing or purely decreasing graph. This is a curve that you need to understand with the help of neural network. So in the beginning, the farther we got from the city center, the cheaper the prices. Okay, the reason why this looks like this curve is because the further we get from the city center, if the hotel is far from the city center, the prices becomes cheaper. This is expected because there will be a higher demand of hotels closer to the center. But there is a point in the middle where the room gets more expensive, or the further we get away. The reason is that the resort type hotels charge similar or if not higher prices. So these are the hotels which are far away from the city but will also charge similar to the hotels which are closer to the city. So we want to understand this non-linear relationship between these features corresponding to the target. A typical neural network consists of three layers, as I said: input layer, hidden layer, and output layer. And in our example, we'll be having one hidden layer with three neurons, and the two inputs that we have is distance and ratings, and the output layer will have price as our output layer. And hidden layer is where we'll try to understand the relationship between distance and ratings to generate an output, which is price. So now let's talk about hidden layers. The number of hidden layers depends on the type of task or data we have. Since we have a small data set, we use only one hidden layer with three neurons, and it transforms the information that it receives from the previous layer into an useful form based on the goal of the task, and it tries to understand the patterns and signals from the data and tries to form the relationship between those features corresponding to that target and tries to update those parameters inside those neurons in each hidden layer. Now similarly, the transformation is cascaded to the other hidden layers until it reaches the output layer, which will receive a summarized relevant piece of information to aid its prediction. So finally what we'll get is a summarized result in the output layer. Output layer has one neuron that outputs the predicted price. In our case, it is for room rate prediction. It will be a final output we'll have. Now, in the previous video, we were discussing about single neuron, where we discussed about weight and bias. Now we have three neurons, so we have to calculate the weight and bias across all these neurons, and also we have one output at the end, and which takes in three inputs, which is from A, B, and C. It has to calculate the weight for those layers as well. So totally what we have is, we have 9 weights and 4 biases. So what we do is we initialize these parameters, which is weights and biases, randomly, and then as we run through the training data set in the epoch manner, then we'll be updating those weights and biases. Now let's talk about the training process. We have already discussed this multiple times in the previous video. So we have come to a conclusion with respect to data and task. So we have features, which is distance and ratings. Target is our price. And we have 32 data points under training data set, and then we have 8 data points for testing data set. And the task that we are trying to solve is non-linear regression. So now since we have our data set and the task that we want to do, it has to go through this training cycle, which is predict, measure, feedback, and adjust. Basically means forward pass, loss function calculation, and then backward pass, and then weight updates. So now let's talk about predict step, where we pass our input data to the neural network. So we have distance and ratings, and we pass that to the three neurons that we have in our hidden layer. So first we have to calculate the z, which is the weighted sum. Then we want to pass that weighted sum to the activation function. So this is how this diagram looks like, where we have distance and ratings, and each neurons is calculating z and a, and we'll be passing that to the final output layer, which is another neuron, which will also has its own set of weights and activation function, and we have to update that as well. So since we have multiple neurons, we have multiple weighted sum and activation computation at each neuron. So for example, if you see here, let's take for one neuron, right? So we have distance and ratings, W1 and W2. Then what we do is distance into W1, which is this one, and ratings into W2, which is this one. Then we have our bias for that specific neuron. We combine all together to get Z. Now, since we talked about linear activation, what it does is whatever the input you give, that will be the output as well. So it doesn't change anything with respect to your input. So Z is passed to the activation function, which is equal to again Z. So linear activation, A is equal to Z. Now let's talk about another example where we have three features instead of two. Now along with distance, ratings, we also have pool, if the hotel has pool or not. Now there are three weights corresponding to those features, which is W1, W2 and W3. Since there is still only one neuron, we have only one bias. So what we do is we multiply distance with weight W1, ratings with W2, pool with W3. plus b, which gives you z, and if you are passing it through the activation function, which is linear, then a is equal to z, and finally we get our output. Now this is with respect to the forward pass, where you calculate the weighted sum and then pass it to the activation function. Now you have gotten your output. Now you want to understand whether your output is good or not. So what you do is you compare it with your actual or ground truth. So what we do is consider you have some predicted value and corresponding actual value is present. The difference between these two is called as error. And what we do in our example is we calculate mean squared error. So what we do is we square the value of the error. So we measure the performance of prediction results. We use the same loss function, which is mean squared error, as we did in the linear regression case. And the average squared error overall 32 training point to get MSE. So what we do is for 32 data points, corresponding error value will be present. We'll average that and square it. We'll square it and then average it. And feedback is the third step of the training cycle, where we'll be using the weights and bias and update our, we won't be updating, but we'll be calculating those weights and biases with the help of gradient descent. So feedback is a lot different for multiple neurons than a single neuron has done earlier. So in the linear case, we had just one neuron, so it did not have much idea how things were going on there. So in feedback, we want to find the right parameters, that is gradient, which is weight and bias, so the neural network can adjust its parameters. So we had weights and bias everywhere here across the layers, here and across each neuron we had biases. So we want to update them such that the neural network can understand the relationship between the feature and target. We start from the output layer. Since it is the feedback, then we have to start from the other side of the neural network, which is the output layer, from where we'll be having our loss function or the mean squared error that we get. Okay, from there we have to start. So single neuron in the previous case, right, how we calculated was we had loss, we just passed that and we calculated dw, which is the gradient for the weight. Now we want to do that for multiple neurons in the non-linear regression case. So let's talk about the forward pass computation, what we have calculated, and then we want to talk about backward pass computation. So we had weights, okay, then we multiply that weights with input and we get our matrix multiplication done between I and W. Then we add our bias, which is not present here because we are just discussing about weight for now. What we do is we add bias also and we calculate our weighted sum. Then we pass it to the activation function, and this is the flow for it. Now what we want to do is we want to do the backward computation such that we can update the weight and parameters. So once you are at the end after the activation function, what we'll get is our error value or the loss value from the loss function. Now when you want to go back, what you want to do is you want to update your activation, then you want to update your dz, which is the weighted sum, which will basically update your dw. So in calculus there is something called as chain rule. So if you have this specific value, you can able to calculate dA, and once you have dA, then you can calculate dz, and once you have dz, then you can calculate dw, which is basically input into error. So in this case, if you see here, dw is equal to into dz. Now here we have couple of new terms like activation gradient and weighted sum gradient, which is dz. To arrive at dw, we must find dA and dz. So we have to first find these two values, which I said earlier, right? There is a chain rule that is going on here from loss to dA, dA to dz, and dz to dw. So we chain dA and dz to arrive at dw using the chain rule in calculus. We calculate the gradient if we know the adjacent gradient to it. So we calculate dw, adjacent gradient is dz, and if you want to calculate for dz, the adjacent gradient is dA. So we know the loss value here, using which we'll compute dA, and from dA we'll compute dz, and then we'll compute dw, the error term which we referred earlier in the gradient descent to dw. Now let's talk about backpropagation. Now we have seen that we want to update from loss to DA, DA to DZ, then DZ to DW. Now this has to happen across the whole network. So we have 3 neurons, okay, in the hidden layer. So we want to do this for all the 3 neurons and want to update our parameters there. So starting from the loss value, the information flows back to all the neurons so that each weight receives its gradient. So dW is the gradient that we want to calculate, and then we want to update our initial weight. So first loss is present, then we calculate dA, from dA dZ. Then we have our 3 neurons here. This is one neuron, this is another neuron, and this is another neuron. Where with the help of this dZ we calculate dW, then dW, dW. Okay, and dA is from this, right? This is where you have dA and dZ again coming up. This is similar to this one. Okay, this is similar to this one. So once you have calculated here, right, this dW, then we'll be using this dW and then we'll be calculating dA again. Okay. So that's the flow for backpropagation. So this flow looks quite complex. So let's break it down to simple one. Let's ignore certain aspect of the neural network. Okay, now let's look at only one neuron which is present at the top and how the weight update happens there. So we have loss value first, then we calculate dA and then we calculate dZ, and then using that we'll be calculating dW. Now this will generate some value using which you will be calculating dA again. Okay, now using dA then you will calculate dZ, then again you will come back to dW. Okay, this is the whole flow for one specific neuron during the backpropagation phase. Now tracing the line along the graph, we obtain the dW by multiplying the input data I by neurons A's dZ. So we calculate dW by taking the input and the dZ coming from here, you calculate dW. Meanwhile, you obtain the blue dW, we calculate this dW by multiplying the neurons output, which is from here, whatever the output comes, okay, and then whatever dZ comes from here, from this neuron. So that is for the interactive math, right? So if you want to understand the math behind this operation, what you can do is you can go to this specific YouTube channel and understand how the math works. Now in previous video also we talked about gradient, and there are 2 properties of gradient, which is the magnitude and direction. So we'll talk about magnitude as well. Magnitude refers to greater the magnitude of the gradient, the greater the weight update should happen. So consider, right, you have 3 inputs and then you'll have your dZ, which is your weighted sum of all these 3 inputs into weights plus bias. Then you get your Z, and once you do the backpropagation, you calculate dZ. Now since you calculated dZ, for each input you want to update corresponding weights, which is dW1, dW2 and dW3. So larger the input, the larger the corresponding weight gradient. Let's understand with an example. So let's understand in terms of error contribution. So consider you have 3 inputs and one input has a larger impact with respect to the final prediction that is happening. So if that is the case, okay, it means like if you see here, it means larger inputs have greater influence on the output value, thus on the prediction outcome. Therefore, large weight updates or adjustments are done on the larger inputs, which has larger influence. For instance, if you see here, we have 3 inputs, 1, 2 and 3, and assume the one has larger impact on the output. So it will have a larger gradient that we have to calculate, and such that we can update its corresponding weight. So that needs to be done with the help of backpropagation. So here, if input 1 is the largest, it means it contributed the most amount of error. So tell input 1 to make biggest weight adjustment by giving its biggest weight gradient. So we also know that if the input is having a larger influence on the output, that corresponding input has to be updated with much bigger magnitude of weight or weight gradient. Now we also talked about direction in the previous video, where we talked about how we have to update our weights. If it is in the negative direction, okay, if it is a negative value, then we have to increase our previous weight, and if it is positive value, then you have to decrease your weight. Okay, this is the same thing that is happening here. So we have, if it is positive, then we have to go down this side. If it is negative, then you have to go down this side. What is negative gradient? If the weight gradient is negative, then the network will need to increase its weight instead. So this is what I have said previously. So from the previous video, the negative value causes the gradient to flip its sides. Now what we have done is we done it for only one neuron. So this has to be done for every neuron. Okay, so we have to update dA, dZ and dW across each neuron and then get our updated parameters. So example with the bigger network, suppose we have larger neural network with few more hidden layers, then this is how the weight update will happen there. Now let's take the single neuron where it takes the input from three neuron outside or previous layer, and this one then it sends the three output from here. So we want to calculate, once we receive the dA gradients from its output, okay, from this output we get the dA gradients. Okay, then we want to pass that to the next stage or next neuron, layer of neuron. First, sum up all the dA values. So whatever we get here, we sum up all their value, we get it here, then we generate dZ. It represents the net gradients coming from three outputs. Okay, this represents the net gradients coming from three outputs. As per chain rule, dA helps in finding dZ, so we get dZ, and then from there we get our dW by multiplying each input with dZ. Then we get our dW corresponding. So now let's talk about adjustment. So we have calculated the gradients in the previous step. Now we want to update our initialized weight, which was initialized randomly. So what we do is, across each layer and across each weights that we have, we want to update our gradients and get a new weight. So the formula is W new is equal to W previous minus alpha into dW. So in previously we also discussed what is alpha, which is nothing but your learning rate, which will try to help the neural network find the optimal value of gradient or loss function, optimal value for the MSE. Okay. Now let's talk about bias. So till now we have seen how to update the weight. So now we just have to update the bias. For across each neuron we have one bias. So we have three neurons. So we'll have three bias there, and also at the output layer we have one neuron. We have to update there as well. So till now we talked about weights alone. Let's discuss bias, and bias gradient is dB is equal to the error, which is dC. So dB is equal to dZ. So we want to update all the biases with which is equal to the value of dZ, which is nothing but error. And similar to weight update, we have to do something called as B new is equal to B previous minus alpha into dB. dB represents the weight bias gradient. We multiply that with the learning rate and then update our bias parameter. Now once we have updated our parameters like weights and bias, then we want to train this whole thing. Okay, we have to pass this whole training data set multiple times for across this neural network multiple times. So that will be called as epochs. So every time you pass your data set through the training cycle, we complete one epoch. So we want to do this for number of epochs based on the kind of problem you are having. So if you have a like complex relationship, the number of epochs will also increase. So what is the goal, right? So just go back to what we are trying to achieve, which is updating weight and bias such that we can reduce the error. Okay, that's the whole goal of this task. Now consider, okay, you have trained the model, you have run it for 100 epochs or 1000 epochs, and you have trained a model. Now you use that model to do the prediction. Now you see this prediction where there is there is difference between each predicted value and the actual value, and you end up getting a mean squared error of 920, which is high, very high. Okay, then you also test this specific model on testing data where you see MSE of 1020. so which is also very poor. So what we do is we have to look into why this has happened and why it has failed to learn the properties of or the relationship between the feature and target. Now the reason why the neural network failed is because of the activation function. Because what we have done is we have passed linear activation when we were training the neural network, where you give some input, it will generate the same as output also. For instance, linear activation, if you have three inputs like this, 1, -2 and 2, if you pass it to the linear activation, it will generate the same thing outside. Okay, there is nothing it has done actually, the linear activation. So let me read this. It can be shown mathematically that if all the neurons in the hidden layer are using linear activation, they make no difference to the input. They don't make no difference to the input and also the output that comes out of it. So it doesn't matter how many neurons there are, it effectively the same as having no hidden layer, which is equivalent to we had in the previous video. So if you are using linear activation, even though you have multiple hidden layers or multiple neurons in the same layer, there is nothing the model will learn or the neurons will learn because it is sending the input as output. So to understand or understand the complexity of the data, we have to introduce something called as non-linearity. To do that, we have to use some different activation function. So the solution to our problem is to introduce non-linearity in the hidden layer. So with non-linearity, having hidden layers now make a huge difference. The more layers and neurons the neural network has, the more complex relationship in the data it can capture. So consider this, right? You will be, so first what is the nonlinear activation that we are using is ReLU, where you have any negative value, if it is sent to the specific activation function, it will be turned into 0. Only positive values will be kept as it is. So consider we have data input where we have three values, 1, -2 and 2. And once you pass that to the activation function, which is the nonlinear activation function ReLU, then what you have, the output is 1, 0, 2. It turns -2 to 0. So it basically ignores the value which are negative in value. With linear activation, it doesn't matter whether it thinks a piece of information is important or not, it just let it through. But with ReLU, every neuron can make a difference. It can now choose to only activate when the input is positive. So now we understood what will happen, right? If you have ReLU activation, you will only take in the positive value of input and all the negative values will be ignored. So what we do is now we update our neural network in the three hidden layers, not the three hidden layers, in three neurons in the hidden layer, we'll be updating the activation function as ReLU. And in the output layer, we'll still keep it as linear. And let's see what happens after that. Now, once you have trained a model on non-linear activation function, so the MSE tends to reduce to 50.4 and the distance between each of those predicted values is very less now. And similarly, it goes for the testing phase as well, where we have reduced it to 70.4. Now, if you want to further improve the performance of your model, what you can do is you can add one more layer and add more units to that hidden layer, and then you can train the model again. So once you have more number of layers and units, the graph that the boundary or the decision boundary that gets generated or the prediction that is happening, it gets improved by a lot, and the prediction will be much more granular in nature. And let's talk about activation function. We have just talked about linear activation in previous video. Now we'll talk about ReLU, where we ignore the negative values and get the output. There is also something called a sigmoid and tanh, which will try to understand complex relationship again and generate values in a certain range. For instance, sigmoid will give you value between 0 and 1, and this tanh will give between -1 and 1. So we have seen a lot of things in this video. I hope you understood how deep neural network works with respect to nonlinear regression. So we'll see binary classification in the next video, where we'll discuss how to use sigmoid to get the probability score between 0 and 1. So with that, I'll be concluding this video. Thank you for watching.